So this week is, I'm going to go over. This week is electronics production, as you know already. This means that you will learn how to manufacture electronics in a Fab Lab setup. But we also give you these classes with some concepts of electronics to get you started already into the dynamics for electronics, and that when we get to programming or design, you already have the basics, let's say, at hand, and you know what things, what are the physics behind electronics, like voltage, current, resistance, etc., etc. So this session, even if it feels a little bit like out of scope now for this morning, because you've been touching and soldering and doing these things, it's very useful for you to start talking about these things and have them in your brain for 2 weeks until we start seeing the design class, okay? So you have this in the documentation, the class. I'm not gonna use the material in the class. For those that are at home, I'm gonna use mostly this whiteboard. And if you guys have Arduinos and resistors and LEDs and these things, at the end of this hour, we're gonna do some examples, hands-on examples, that you can find at the very end of this class, of the page, okay? So having said that, let's get started. Please interrupt me if you don't see properly the whiteboard, because I want to know. Things to remember. So things that I want you to get out of the session and know. What is voltage? What is current? What is resistance? And ultimately, how they relate to each other. Okay. First one. So you see the, yeah, right? Do they see the what? Maybe Samsung. So first thing, anyone that knows what voltage is?
And watts.
Amps times ohms?
Watts.
Watts?
Yeah. Watts.
So that means that we have amps, which is current, and watts, which is power.
Yeah.
That is not entirely true, but it's somewhere near. Let's go to a more like physical level, let's say, of these things. What provokes voltage?
Electricity, energy.
Energy, okay, that's not bad. Energy where? In the atmosphere, in my keys, on the whiteboard?
No, energy in from a source to an input and output. You have a source that creates energy.
Okay.
And it transforms this energy in a power source.
Okay.
And this power source will give you a voltage.
Okay. The only thing that we're missing there, besides some things that if there was a physicist here, they will kill us, it's that we need a material. Okay, we need something where the voltage is created, which is wood, plastic, metal, anything, okay? And that material, we're gonna just make it like this. And we're not gonna start zooming in the corners of the materials and see what do we have here. This is materials are made out of, or let's say, matter is made out of atoms that are some things. Some of them have different shapes than others.
Okay.
But if we look into each of the atoms,
We have protons and we have electrons.
we have protons and we have electrons. Protons are in the what we call the nucleus. And
Electrons are around,
electrons are around, perfect. So we have some particles here that we're going to call electrons.
and ions, negative.
They are negative. Perfect. So they have negative charge. In the nucleus, we have
Protons.
protons. That are
Positive.
positive. One thing that we didn't say earlier is protons, so positive and negative.
And you have ions that are neutral.
Right?
Ions.
No.
The
Okay.
ions.
What does happen? Do they go away? Do they repel or
They create a source of energy, electricity. They repel each other.
they what?
They attract and they attract each other.
They attract each other? Negative,
They repel each other.
positive, they
So,
repel. Right? So in the atom, let's say we have some electrons, some protons in here, and you will say, if we have protons in here, how is it that they don't come apart? There's something else in the nucleus that is called the third chemical
Ions.
particle.
Ionics.
No, it
No?
starts with N,
neutrons,
neutrons,
Oh, yes, neutrons.
that are, which are
No.
positive, negative,
Neutron.
neutral, exactly. So they have zero charge. So here basically we have a bunch of protons that are held together with some neutrons in the middle. Here we have some electrons floating around that are just like moving around here, attracted by the protons. They stay around there, right? Now electrons are free more or less to move. So if we have material that allows them to move in out, which is called conductor. Examples of conductors,
Cooper.
copper,
copper.
Yeah.
Now it makes sense why all electronics are made out of copper, or wires are made out of copper. Other
Carbon,
aluminum, maybe,
aluminum,
and in general
metals.
metals. So metals allow conduction. Conduction means that electrons are freely moving inside the material in a cloud, let's say, which are like around here doing their thing, just somewhere, floating in the space. And you said earlier that if we supply energy to a material, and we are able to take electrons to one side and accumulate them in one side, imagine that in this material there are all those pairs, and all of a sudden we manage to accumulate them on one side, and then because nucleus are fixed, let's say, this side we have what we would call lack of electrons or positive charge. Yeah. This here makes a difference between negative and positive. And this is what we call
current,
No.
voltage,
Voltage.
So if we have a material, we put some energy in it. We're able to pull the electrons in the material and accumulate them on one side. And we keep them here. In that state, in that situation, between the negative side where the electrons are and the positive side where the electrons are, there is a voltage. Okay?
So they produce energy.
We need to put energy, and that's why we have plugs and batteries and connectors and this type of thing, so that we can put energy and make this work. Now, imagine that we let these things move freely. What would they do?
They create energy, a source of energy.
We're putting the energy, but what if I let this move? So I stop putting this, what happens with the electrons? Do they stay here or do they move?
No, they move to the outside and they will try to,
They go back to seeking, let's say, an homogeneous state, right? So they go like that, and the electrons move. What happens in that case? What do we have?
they will be attracted by the,
Good.
A current. We have current, which is electrons moving because of voltage. The last question then will be, what happens if we somehow restrict the movement and we don't let the electrons move freely inside the material?
resistance.
We did something like this, you already say. This is what we would call, or the effect of this, let's say, is what we would call resistance. And the more resistance that we have, do we have more or less current?
Yes.
Less current. Okay. And if we have less resistance,
More current.
more current. That's. And then we could say that voltage, current, and resistance are all related somehow. If we have voltage and we have some resistance, the amount of current that is going to go through is determined by this law or this equation. That is, someone knows it already? Ohm's law. Okay, that basically states what is the relationship between voltage, current, and resistance. Now, units for each of these.
What's
Voltage is meant
Both.
volt. Capital, uppercase or lowercase? Uppercase or lowercase?
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 No, uppercase, uppercase.
Uppercase?
Yes.
This feeling that you have now is going to be magically solved now. If the units come from the name of a person, it's always capitals. Volta is the person that discovered voltage. That's why it's as its name. So volts are capital V. Current is measured in amps. And it's uppercase or lowercase?
Uppercase.
Uppercase because it comes from
Ampere.
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 Ampere. And then resistance is this guy,
Ohms.
ohm. So it's ohms. But if we made a capital O, we wouldn't be able to distinguish that from a zero.
Oh, from oxygen.
So we may put this,
Yeah.
which is big capital Omega. That maybe is like omega ohm. I don't know, maybe it's just my way of thinking. So we already have the current, so we already have units, we already have the law, we already know how the physics go.
And it's quantum physics.
Let's start thinking about a very
Smile.
Can't.
Smile with your eyes.
Wait.
Like this.
Okay. Listen, can I erase it?
Yeah, thank you.
No. So now we know voltage, current, and resistance. Let's see if we put that into actual something that is actually useful. So imagine that we have a piece of wire that is made out of copper, for instance.
Mhm.
And we put some voltage in here. This is the positive side, this is the negative side. We're talking about voltage that is DC, which means is continuous or constant. And it's always like this. If we're not gonna see yet the opposite, which is AC, which basically is positive, negative, and then negative, and then positive, and then positive, and then negative. It's oscillating
Alternate.
all the way. So it's more like this. This is called AC, and the frequency at which oscillates, normally in the plugs in here is between 50 and 60 Hz. So it means it's changing positive and negative 50 or 60 times per second. Okay? We're not gonna see this yet. We're gonna assume that we have input of power, as you very well said. You need to put power. You need to supply power to the circuit. So this is called, if it supplies power.
I'm not the only one here, you have.
Okay, if it supplies power, if this thing supplies power, how do you call this thing? A power supply? Right?
A power.
Do you like that name? Power supply, because it supplies power. It's quite good, right? Sounds about right. So we have voltage, and then in here we know that if we have some voltage and we have some material that is conducting, then we will have some current flowing through, right? Now there's one thing missing here in this circuit, and you all know already what this is. Is this, right? What happens if I don't put it in? If, let's say, voltage equal current times resistance, and let's make this little table. This is 5 volts. This is 0. We assume that this is 0 ohms. What is the current going to be?
It's gonna be 5 because everything is gonna be.
So let's take it out. So it is I is equal, so it would be 5 divided by 0, which is 0.
No, it
No, you
didn't
can't,
exist.
because it's about those.
It does not exist, it's infinite.
Infinity. So it means that this is super high, right? Which means that this current is super large, which means that this confirmed. Why? Because current, when it's very large, we have what we call short circuit. And you many times will see this with this sign. Maybe something like this. Danger, because this can kill people. Very large currents can kill people. Okay? So in this situation, if we don't put a resistance in here, we will have a very large current and people will die. But if we put a resistor in here, let's imagine that this value, this resistance is 5. This is still 5. This is 1 amp. Perfect. Now, how can we visualize this thing? We're going to start by making an exercise with your Arduinos there. We're going to visualize the current that goes in the circuit by putting a component called that will react, let's say, to the amount of current that we have, and will shine more or less depending on how much current goes through. So the first exercise that I want you to do is this one here. Actually, in this one here, but instead of putting it to 9, put it to 5 volts. Okay, I didn't realize this, but you have to put this cable in 5 volts. And this will make you supply voltage to a circuit that has a resistance and something that makes us see what the current is. And what I want you to iterate is, first question is that what happens when I change the system? Okay, so what happens with the lights of the LED? The LED. When I change the resistance, okay? I assume that, well, you will see the relationship that if it's 5 and then this value, for instance, is 1 million, then this value will be very small. And this guy will sign less. Okay? Let's start, and then we'll be making this circuit a little bit more complex.
Okay, positive and 9 and negative and what?
Negative, the negative is ground, positive goes to 5 volts. Okay? LEDs, one comment. LEDs look like this. LEDs look like this. And they are represented with this symbol.
There you have the LED.
This is the anode
No.
or positive side.
Yeah.
This is the cathode or cathode and negative side.
The other one.
Anode, cathode.
So negative to positive is the first one, no?
Okay, so the LEDs have one leg that is longer than the others. Positive, negative, positive, negative. You will see that if you put it wrong, current will go that way, but it doesn't go this way.
It's row. In which it's today.
People at home, do you have Arduino on this type of thing?
Why it's not in the same line? From positive?
Because this we will see that it's a more complex circuit little by little.
Okay.
And I made the complex one first, and then I started removing the
Okay.
parts. But the principle, instead of looking at the TV, I want you to look at here and try to make this on the ground.
Okay, so it can be in the same line.
Exactly.
Okay.
Just so people at home also, I don't know, I know that you guys have seen with me how a breadboard works, but maybe
I have to be in the
Here.
same line because
just to remind us.
Here.
no. It's going from positive to the first line. Okay, the first road or line. Which are lines and which are roads here?
So for the people that are at home, someone here can explain how breadboards work.
So
Here.
this one here.
How are the traces connected? Or there, anyone remembers?
What?
Breadboards?
Are
How, here, how,
positive. Are positive.
but how are they connected? Vertically. So these are connected like this. And the other ones in the middle, like, are the same or how?
No, the others.
Okay. So they go like this.
Yeah.
And there's a gap in the middle. So this side is not connected to the other. Okay. So if these ones are vertical, if these ones are horizontal. Power supplies, if you don't have your laptop, you can use these cables with the chargers. They are got 5 volts. Okay. Explain the diagram. This one here, this is extra. You don't actually need it.
Okay.
positive, you can connect it to this leg. This is like a little, like zigzag, let's say, is the long one, which is the positive. So positive to positive, negative to the resistor, resistor negative.
The long one is the positive.
The long one is the positive.
Positive.
But that is not an LED, that is a capacitor.
Oh, this one.
That, yeah. And normally LEDs, there are like different types. The one that we want is the one that has 2 legs.
So you need to do
If you have one that has 4 legs, that is that has 3 colors in one. Okay. But for now, it's just
Oh, you have it like a table where you have the number of the resistance. Tienes la tablita o tienes los números de resistencia, pero no resistencia. Eso. Ok, entonces la que estamos usando tiene una negra, una verde, una
to put it
amarilla.
in here.
Yeah.
¿Quieres que lo ponga aquí? ¿Cuáles son? Dime.
Ese de aquí entonces es de 4.
Dime los colores si quieres.
Tiene
3 o 4 bandas. O 5.
la mía es malísima, no veo.
Here what we are seeing as well, if you want to know the values of the resistors,
Okay.
you can go to a table like this, and it gives you the values. You see it in my screen. This is a table that describes the color band of the resistors for the resistors that look like this type. Let me see.
On the line is too bad.
You don't see it.
Yeah, some
You don't see,
light.
well, you can see it in here in the image on my screen. They have different colors that signify different values. And there are millions of online calculators for knowing what the color code is. We'll see in electronics design that there's a lot of different formats for resistors. And some of them don't have colors, but they have the number written on them. The important thing is that you should be able to identify what the value is, because that is what is going to limit the current on your circuit.
Okay, this one, red, like that, black, right? Yellow.
Is it? Okay, so it's café negro rojo. Café negro rojo. So that is 1 kilo.
This one.
Okay, does it work? Can you plug
Creo que no
it?
es la misma.
Did it work?
No, no es la misma, mira. Tiene otros colores. No, it's red. It's not working. And this
Okay,
is
what's
not
maybe is the resistor. Okay, here this LED is connected between nothing and the resistor.
Yeah, because the electricity must come here, right?
Exactly, but this is not connected. Maybe you don't need this table, maybe. You just can simplify that.
Yes, these have to carry the same line that you are using for the current.
So the resistor is connected to the negative.
But they are connected like this. You can keep it like that.
If you wanted to connect this to the,
And now you need to bring this cable to connect that. Right?
you want to connect to the negative.
So the same load.
Do you guys see, do you have materials at home to do this? Right now or not? Hello?
To connect these two.
Hi,
Yes. Do you have the material, like an Arduino Uno or something to do this at home?
I have a special of training. Maybe I can.
It doesn't matter as long as you have like Wow, that's really, really complex. As long as you have 5 volts.
Yeah.
The idea is that the only thing that I want today is to visualize, let's say, this like Ohm's law somehow by changing the value of the resistor, and then we're gonna iterate a little bit and make it a little bit more complex, okay? So,
¿Cómo era? A ver, tenemos el negativo que está yendo a ground.
negativo está en ground, ¿sí? Correcto.
El positivo está en
En un pin que ahora mismo no sabemos si está funcionando, lo pondríamos aquí por el 5 volts.
no veo.
Oh, yeah.
¿Vale? Ahora, el positivo lo tenemos aquí, pero de aquí a aquí no hay conexión. Queremos ponerlo aquí. Ahora, positivo, 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 and now,
So también
de este lado, from this side to this side, there's no connection. So we need to be both sides. They're connected like this, but not on this.
So it's supposed to be negative, so ground is negative.
Okay?
We always connect the negative.
So let's
this is the main one.
goes 40, sorry, not 41. 5 volts. Now I have to think that maybe there is a cable. There's maybe a cable that is not liking it.
What do you
Yeah.
think is the
It's not connected.
The negative is wrong. Yeah.
No,
Because the lead
And
is
then
no
the
resistance.
middle.
maybe
The
I
resistance.
think we have to change the different cables and
This is
see
the
which
blue
one
one
is
is the ground.
making the problem.
Yeah. Thank you. That's it. No, this is the
Positive. So let's see if we find something important. Maybe we can try different LEDs.
The lead starts working.
I have it on
It shines
ground.
for a second because
I know,
it made a
right.
short, so then now it's dead. So maybe let's try to change. Yeah.
Oscar, can you ask a question?
This is the positive. Then you connect another one.
What's that?
Where ground.
Maybe there is a switch.
So this is
We
the
are
positive two, huh?
Yes.
When does it get negative? The blue is
They are- We put them on the same line, let's say. It's like we have the electron LED, but in parallel, we have there's actually no voltage. Right now, they are connected. The resistance,
So usually you
negative,
use like
negative.
a
So that should work now, but probably now we either have a problem with either the cable that is on or that the LED is
This is the positive.
Oh, yeah, let's try to go to different ones. Where for different resistors as well, I can give you some.
This is negative.
Yeah, these communicate. These communicate to the
En este no hay cantidad, no, esto es un diode que vamos a verlo ahora. ¿Ok?
¿Cuáles son los
Did,
work?
did any of the LEDs work? No?
No.
Not yet? Really?
No.
Did it work or not? You can try.
So maybe-
Another resistance, can we change all the resistance of the cable?
maybe grab some other examples.
Yeah, but probably we don't know which one.
But you put it on the next.
Of
It's
the.
not working.
Do you want to send everything or not?
It's a short one.
Then we're gonna try like, maybe let's go with like.
Okay.
Okay, yeah.
That's,
We have to bring them ultimately. That's also.
Maybe it will go together.
This way is that. I don't know why, but I don't.
No, it's not mine.
How you change?
what's the word? The word of the word.
Yeah.
Change it. Maybe change it.
Yeah, we need to do it for the next.
There might be some bad connections, but believe me, this will work. Okay.
Yeah, it's working.
It is very dim. So maybe try to remove this resistor and just put as if there was an end. It will be dimmer. I'm sure that this LED will survive if you put it in here. Okay. And there's still, it doesn't die when you increase the resistance. Comes lower, right?
Yeah. It's working.
So what happens? What we are doing, now we are maybe orient. Can you help me with focus? So does it work now? If we increase the resistance here, this value, we increase it as we go this way, the amount of light that we have is much smaller.
Less, yeah.
Because, well, not this one, but because of this equation, right? At some point, we'll get to a value that is so large, here, that here is so low, and it doesn't shine at all. And that happens when we have that. This is called normally open circuit, which means that there's no current flowing because the circuit is open. It's the same as having a switch and have it open. Okay. Now we're gonna see another component that we're gonna put in here that is called a diode. It's very similar to this guy here, but it doesn't emit light. Okay, diodes normally look like this, and they have a line in here. This is the anode, and this is the cathode. Current only goes that way, but doesn't go this way. Okay, this doesn't work, and it only allows current to go this direction. What do we use this for? Normally for protection, so that there's no reverse current going into our power supply and we kill our computer or our charger or our Arduino or things like that. Now, I want you to try them. They look like that. They normally have this package. I think that people at home won't see it, but I can put one in here. And you'll see that there's a silver stripe, let's say, on one side, which marks the cathode, which marks the direction, like that. Okay? So I want you to try this here and turn it, flip it, to see if it doesn't. Okay? For those at home, diodes look like this. This is exactly what I have in my hand now. And basically the stripe on the silver stripe is the cathode, which is normally the negative. If you try to put current on that side, it won't let it happen. It won't happen. So it will, let's say, protect your circuit. Okay. If you have one at home, please try to put it in this side. Also, let's try to answer these questions. So the questions for these are: what happens if I put it like this? What happens if I put it like this?
But instead of the resistor, do we put it or?
With the resistor. Sorry,
With the
resistor. This basically just stops or not, or doesn't stop. And what happens if I put it in here? You change the setting. Okay? Try fourth position and let me know what happens. Okay?
So, to the left or to the,
So you have to put it either from the positive to the resistor or from the resistor to the negative.
let's see.
You first might want to take this cable out. You need to put from the resistor
everything, yes.
to the side that doesn't have two lines, doesn't have to do.
No, we go to eight. Yeah, it's not.
To the negative.
I took the resistor.
There you go. So this is our negative now. And you have to connect negative to negative. In the blue left side, right? These are there you go. So current is going through here, through this side, through the diode, because the negative side it allows current to go out. If you turn it, what happens?
But if you change the resistor,
Make the. Okay.
So if you turn it, it even jumps. It becomes a light. And if you put it in, the diode is like a door that doesn't let things go this way or the other way. And since we have the positive here and the negative here, and this is, let's say, the dot that we're closing, so it doesn't go and the light doesn't come. Now, what happens if you put it on the other end of the circuit? You see, it's not in the positive, it's not in the negative. If it's on the negative side, you put it on the side, it's equal to power, and then
Like the, when we did it, the light.
oh, if you just flip it,
That was it, right? No?
if you put it on the other end, so now you have it.
Because the positive, like, it's supposed to in this direction, and this is the negative, right? And so right now, negative.
change the order of
LED before, now you have LED before diode. What happens if you put diode and then
what do I have right now? I have
you have positive LED diode?
okay.
I want you to put positive diode LED.
Can someone have any difference put the resistor? Like when I put the resistor, then obviously the light way. It's negative.
But wait, I cannot change that into result.
Yes, sir.
Yeah, it turns out.
Positive, positive.
So what we are saying here is that what we want to do is
We just lift like the, like not the resistance, but the diode, it's just like.
why not?
Yeah, that's it. No. Yeah. Oh, it works with the resist with the.
So what I'm asking now is what happens if we have this option or this option? Does anything change?
Right now it's
What is
negative and
positive
it
and what
works.
is negative?
This is positive, and this is negative. Let's say that I am unfold the secret, and I just put it like that. Does it change?
No,
It's exactly the same, right? So this means that the components are in what we call in series. Which means they're one after the other, and nothing matters. The current here is the same as the current here. This one and this one are the same, and it doesn't matter in which order we put them. If the diode is before or after, it has the same effect because they are what we call in series. Okay. Now what we will see is that what happens.
What do we? Okay, thank you.
What happens if we have the opposite of in series, which is parallel? Which instead of that, we have something like so these are connected, and this is the negative, and this is the positive. Right? So in this case, things matter. I cannot switch this thing, this, and put it here because I changed the circuit. Now, what I'm doing is that the current that I had before, that is this current here, when it gets here, what happens with it? It will divide, okay? And it will split between one side and the other. And what is the relationship between these? What do I put here? Do I put like multiply, minus, plus, divided,
Yes,
root square,
yes.
plus? So they sum. This one and this one, if you think of it from what we were seeing earlier, we have electrons moving in the material. Electrons don't come from the outside of the material and they don't leave. They stay in there. They just move from one side to another. So here, basically electrons are moving and they split it into two sides. How much goes into each side? Well, then we have to come back to our friend. Let's put it again like this. And let's think a little bit together. So, positive, negative, this is our voltage. We have some current in here, I1, I2. We already know this. The question, the $1 million question is, what is the voltage between here and here?
It's the same question, like E1 and like the L1, E1 and.
Okay, so let's say, so this here is I1 times
Yeah.
R1, and this one here is
I2 times
I2
R2.
times R2. But thinking a little bit, if this is V, this is equal what? What is the voltage between here and here? Knowing that this is just a piece of cable.
Divided by the voltage.
It's just V. This voltage is here and here is the same. Okay? So we know that we know this one because it's what we put. These values we know them because we have the resistors at hand. So we are able to know how much goes to each side. Okay. The second $1 million question is,
That was $1 million question.
what is the meaning? You didn't answer it. The second $1 million question is, let's imagine that R1 is equal, R2 is equal R. This is R. Which LED shines the most?
Which what?
LED of these ones shines brighter.
Right.
Shines brighter.
Which of all of them?
The same. No, wait. Number B. Letter B.
Number B is also one, right?
Sorry?
Number B is also.
I would say the first one because there is more power going to the first one, but I don't know.
I have a mixed opinion.
But you don't have a resistor B, right?
Well, no, it doesn't matter.
So this
It
is-
doesn't matter the order that you put it in.
Oh.
It's too stereo. Too stereo.
Exactly, that's in series. Let me just put this in here like that.
The second one.
My question is,
Ah,
is so 1, 2, or 3, who is the brightest? Knowing that B and B are the same, R1, R2, and R are the same.
Oh, 3, I think.
3.
3,
Because there's less.
vote for 3, this is $1 million. You have to think of it very well. Which one is right?
Because it's a shorter circuit. But you have to say it also. You cannot just guess.
You have to justify
Yeah.
why.
But it's different because this one, the first one is parallel.
Let's think a little bit more.
It's
Let's say
because you have I1 and I2, and here you don't have I.
let's make things a little simpler. What is the equation that we have in here?
Okay.
What is the equation? Tell me.
I,
E equals I times R.
Okay. What is the equation that we have in here?
B equals the parentheses I1 plus I2 times R.
How about here?
So I1
I1.
I1
times R.
times R. Okay, we both agree. I mean here, you already have it here, but let's put it V equals.
I2 times R.
If it looks like a duck, and or how does it go? If it looks like a duck and it sounds like a duck and it tastes like a duck, this is the same, this is the same, these are the same, these are the same. So this is the same. So all of them sign exactly in the same way. The only thing that changes here is that this one here, is
Parallel.
or let's call this I total, I2, or so this one is twice as larger than this one, right? And you have the same. Now this changes things a little bit because you have things in parallel and you have to then consider that current splits and then things can get a little different if you start switching things around. Let's put another component. We're gonna forget about this. Forget about all these equations and $1 million questions. I keep my $1 million. Thank God. And we're gonna talk about a different component, which is called the capacity. These guys look like.
No, there is also.
You stole the other one? Capacity.
We don't have a capacitor.
You don't have it there, but I will give you one in a second. So they look like this. They are different types. Some of them look like lentils, like these ones here. You can pass maybe some around. They look like lentils. Oh. There you go. They look like lentils and they are called ceramic capacitors. Basically, what they do is accumulate a little bit of charge, a little bit of voltage, and then whenever they can, they just discharge it into the circuit. They are this type here. For those at home, they look like these ones here, the lentil size, more or less. The other ones that look like batteries, more or less, they're called electrolytic capacitors, and they have polarity. Very importantly, one of the sides is the negative and the other one is the positive, and is marked in the capacitor itself with a small band that has minus drawn in there. So it's quite obvious. It's also white and it's a convention. So you will see that the negative side is very clearly marked. Why? Why is it marked? Because it can't explode.
Like batteries?
Sir?
Those are batteries?
No, they are capacitors. They operate like acid batteries, like old ones, but not they don't have the same principle. If you open this, or if you open this one, you will see something like electrolytic capacitors. They have like different layers inside, like an onion. And the negative side is connected to, let's say, these layers. And the positive is connected to the rest. So imagine this is positive, this is negative.
But they really look like batteries.
They behave somehow like short-term batteries. Let's say they accumulate the charge, but they don't hold it for much time.
Okay.
Basically, here we generate some voltage many times. So we have like, imagine a very long, if we unfold this, we have positive and negative, and they generate voltage across two layers of material that then discharges into our circuit. The other ones, the lentils, they look like this, and if you cut them here, they look like something like this with different layers of ceramic material, and the principle is more or less the same. Okay? This is positive, and this is negative. Basically, they accumulate charge. It's like a bucket, and you accumulate when you put water in it. It accumulates. If you make a hole in the bucket, then it spills into the room. The bigger the hole, the bigger the amount of current. Okay. Why?
Can you use this? Can you use this under the water?
Sorry?
Do you use this under the water?
No. If you put,
But because
if
they're
you isolate them, you could, but no. So why do we use capacitors in our circuit? Basically, to accumulate some charge. They are normally used for filtering. Because since their accumulator is like a big, let's say, amount of voltage or energy that gets stored in there, and they're able to, let's say, when your voltage is very like this, it basically stabilizes. Don't worry about that. If you put one in parallel here, what will happen? Maybe we don't have time. No. It's up to you then. Well,
He loves stressing.
Oh.
He loves stressing.
so when you have power in here, there's voltage going in, the LED is signing, the capacitor is charging. If you remove this, the capacitor is charged, and then it will discharge through the LED. And the LED will make a nice fade out that will go like, and will be like powerful and then dims. And so on. That happens many times with power supplies. If you have a power supply like this one, well, not like this one, but that has a small indicator LED, you see that it fades out very slowly. Why? Because there's a lot of big capacitors like the fat guy over there a lot of them put it inside because you want to clean the current that goes into your laptop, for instance, because you don't want to kill it. Okay. Now, this will start through here. If you make this exercise with one of the capacitors and you put
So where is the capacitor in that drawing?
this,
Oh,
this is the capacitor, and normally they are represented like this or like this. Normally these are actually they're represented like this. So this is ceramic because there's no polarity. I don't know how the symbol goes in here. These are electrolytic because this is the negative side. Okay, these have polarity, this one.
The
Now-
electrolytic ones are made of lithium.
No, they're made out of like a mix of, let's say, electrolytes that is normally something like water and salt, or salts inside.
Yeah, but lithium is in salt.
Huh?
You can find lithium in salt.
Yes, I mean, but it's like there are, actually, how this is.
Okay.
There are different types, like electrolytes. It's basically, it behaves like water with salt. So the exercise, and I let you go also because it's 2:15. Is that if you go into the website, you can try to reproduce one of the circuits with a switch and a capacitor, and you will see that when the switch is closed, the LED signs. Because basically we have the same thing, the same circuit as you had before. The only thing that we added is a little bit of filtering. You won't see much. When you open the switch, this disappears, and then this capacitor is charged. And it's connected to the LED. So then it will discharge through the LED. And you will see how the capacitor, even if you don't see it visually, it discharges through the LED and makes this nice fade out of light, of brightness until it's totally discharged. You will also see that if you do this, you charge it. You take the capacitor and give it to him, for instance. If he puts it in his circuit and the switch is on, is open, the LED will still dim because this is charged. Okay, that's why they recommend that if, for example, you unplug that, you unplug my charger, you don't touch the plug itself because this still holds a little bit. It's not, it won't kill you, but you will feel a little bit of discharge in your fingers because these are full of capacitors that haven't discharged because the circuit is open. Okay, so you can try the circuit, and then let me know during these days with the capacitors here and around how this works. We will have, so we're gonna close it here today. We will have more of these things in electronics design, but please try to iterate a little bit and make these basic concepts be, let's say, in the back of your head, so that you, when you have to design electronics in some time from now, you already have some concepts and that these things are rolling already.
So
Okay,
the capacitor is the thing like black.
this way.
Yeah, and the other thing.
And this is a switch. Yeah.
Thank you.
Okay. So sorry for the extra 20 minutes.
Great.
See you. Oh, see you. See you.
Bye, guys.
Hi, thank you.
So confusing.
Bye.
Bye.
The guy that was in our office. Yeah, I have to reach him every day. Where's the stuff I always